Good morning, everyone. Today is lecture number 26 of this heat treatment class. And today's menus are overall transformation curve and prior knowledge to the heat treatment of steel, Cct diagram superimposed on Ttt diagram, and concept of hardenability, that is important characteristics of steel. So in the previous lecture, we have been looking at the Ttt diagram and its importance also, right? And why the Ttt diagram is of C kind of curve. And if you look into different textbook also, they have written that it is an S type of curve, but basically we call it C type of curve. And what is the reason behind that? Already we have discussed that. So we need to discuss about this overall transformation curve today. Just I'll show you the overall transformation curve. And second topic is prior knowledge to the heat treatment of steel. So that means before going into any kind of heat treatment, what should be the prior knowledge you should have? That is important. And this is not in terms of the dimensions, or basically not in terms of dimension. And today we'll discuss a new diagram, that is Cct diagram. Already we have talked about this Ttt diagram, but we will discuss about Cct diagram by taking the help of Ttt diagram only, so that you can easily differentiate them also. And we'll discuss about the significance of this Cct diagram. And concept of hardenability here, it is a very important characteristics of steel. Is a kind of property, you can say, which will be very helpful for the heat treatment and to get desired properties also. So this is a figure showing you overall transformation. So you can see this is the temperature axis in degrees centigrade, and this is the rate of transformation. This axis is showing rate of transformation. And this is, you understand, this is a lower critical temperature, or you can call it as a eutectoid temperature if it is eutectoid steel. But this is called lower critical temperature A1, right? That means above this one, austenite is a stable phase. Below this one, austenite is unstable phase, right? If it is an eutectoid steel, that's all. So the overall transformation curve is like this. So that means the temperature near to the transformation temperature, A1 temperature, you can see if we are moving down, that means we are decreasing the temperature, or this is called, you can say, we are doing more undercooling of the steel below the austenitizing temperature. If you are doing more undercooling below this A1, you can see the overall transformation is increasing with decreasing in the temperature, right? So initially the overall rate of transformation, the rate of transformation is increasing with decreasing in the undercooling. Sorry, I mean increasing in the undercooling, right? So rate of transformation increases with increasing in the undercooling initially, or in other words, you can simply
Sir,
say,
Sebastian is requesting to join, sir.
is he joined?
No, sir.
I'm not getting any kind of request. Ask him to join again. So you can see here, that means with decreasing in the temperature from this equilibrium transformation temperature, the rate of transformation initially increases. It reaches to the maximum value. Then again, after certain temperature, from suppose this is the midpoint, after certain temperature, when we decrease the temperature further, the rate of transformation again decreases. Right? So this is the trend actually. This is the overall transformation rate. This can be justified with the help of rate of nucleation curve and rate of growth curve, right? Rate of nucleation always depend upon the driving force. If driving force will be higher, that means if undercooling will be higher, then rate of nucleation will be higher, right? And rate of growth depends upon the temperature, right? Because it depends upon the diffusion, rate of diffusion, right? And if temperature is higher, then diffusion will be higher, then rate of growth will be higher. And as I told in the earlier lecture, the overall transformation rate actually depends upon both rate of nucleation and rate of growth, right? Or in other words, I can say overall transformation rate actually, or kinetics of overall transformation depends upon the uh, the driving force as well as the rate of diffusion. I think this part is clear to everybody. Then prior knowledge to the heat treatment of steel. So we are not talking about anything about the dimension, because you understand, uh, because the heat treatment temperatures also depend upon the dimensions, right? Or the holding time also depend upon the dimension. But here, what the clear idea of phase diagram of steel? Yeah, this is very important. So you understand, that means suppose you have a steel, that means at least the received steel, you should know the chemical composition of that. That's the first criteria, right? You should at least know the chemical composition of the steel if you are going to do any kind of heat treatment, right? And understand, in maximum heat treatment, we have to take the steel to the austenitizing temperature. We have to form complete austenite, homogeneous austenite phase, right? That is the predetermined temperature, if you remember, right? So that means to get where you have a complete austenite phase, at what temperature you will having a complete austenite phase, you should know the phase diagram, obviously. So phase diagram, you should at least you should have an idea about the phase diagram. That means at what temperature and at what composition you will get a homogeneous austenite phase, right? So that can be, phase diagram can be drawn with the help of a software called Thermocale. This is a very expensive software, like 2 crore, 3 crore, like that, or maybe more than that. I'm not sure exactly. So the software rate is very high. So if you give the data like what is the composition of the steel, it will give you a phase diagram, and then you can, and this, that means you can by this help of this phase diagram, you can understand where is your A1 temperature, where is A3, and where is ACM and all, right? Second is idea on Ttt diagram. Obviously, if you remember, you should have a clear idea of this Ttt diagram, right? So clear idea of Ttt diagram means you should have understanding about the kinetics of the transformation, right? At what temperature the transformation start, at what temperature transformation end, or basically, I mean to say at what time actually. Kinetics means at what time, if you're keeping the temperature constant. So at what time transformation starts and at what time transformation ends. And another thing is, TTD diagram also tells about the different microstructures which will form, or different products which will form after the transformation has happened, by isothermal transformation. That means, if you remember, the TTD diagram is helpful to get the morphology and the nature of transformation product, right? An idea of Cct diagram, which we will discuss. Now, yes, now we'll come to our main topic, that is this Cct diagram. This Cct diagram is nothing but continuous cooling transformation diagram. Continuous cooling transformation diagram. So the name itself is saying this kind of diagram will show different transformation product when we cool the steel continuously, right? When we cool the steel continuously, from where? From the austenitizing temperature, right? From the austenite, that means we will take the steel to the austenitizing temperature. Then from that temperature, when homogeneous austenite will form in the steel, we will cool the steel continuously. It will be not like the TTT diagram, like we are cooling the steel in an isothermal conditions at a constant temperature conditions. Here we will cool the steel continuously, right? So that means CCT diagram, what are the things will be available? Will be the things will be available is temperature will be there, time will be there, right? And transformation will be also there, what kind of transformation is happening. But here the thing is what, continuously we are cooling the steel, not isothermal cooling will be happening. So this is the difference, one of the major difference between TTT diagram and Cct diagram. In TTT diagram, we are getting the transformation product by doing isothermal cooling below the eutectoid temperature or below the A1 temperature. But in a Cct diagram, we are cooling the steel continuously, and we are seeing what kind of product is forming. So can you people tell me, this is a question from my side, then which diagram is more important in real situation or in industrial scale?
Ttt.
TTT. CCT. See, if you are saying something, then you have to justify that also. I need who told
Sir,
TTT? Okay, let someone to speak. Who told TTT? Let him answer.
So because in
Yes.
TTT we can also there is some holding time and all. So Bainite is there and
Okay.
like this
Okay.
TTT diagram will be important if you are
Okay. Fine.
making Bainite and all.
Mm-hmm. Okay. Someone told CCT. Can you justify that?
sir, in real case, there is very less process which is done in isothermal way. In industrial scale, all the processes, I think, no isothermal way is adopted. So CCT will be more useful.
Okay. Anyways, see, the point is what, both diagram are actually important because uh, TT diagram have some significance, CCT diagram have some significance, but but in the real situation or in the industrial situations, we are basically dealing with very big size of steels, right? It is not like a small steel in the laboratory scale, right? We are dealing with a very large dimension steels. That is one part, and another part, in industrial scale also we try to do things at a faster rate, right? That means the rate of production should be high also, right? It is not like that will take a lot of time to do the heat treatments and all, right? So basically in the real situation or in the industrial situation, we are cooling the steel continuously. Actually, we are not cooling the steel in isothermal conditions, but unless until we desired Bainite in the steel for some specific compositions, we are not cooling the steel from the austenitizing temperature in an isothermal condition. Basically, we are cooling the steel in a continuous conditions. Continuously, the steel will be cooled. So that's why CCT diagram is more important, because CCT diagram involves temperature, time, transformation, right? And in a continuous way, we are cooling the steel, right? So CCT diagram is more important in the industrial scale. That is the answer actually, right? Because continuously we are cooling the steels from the austenitizing temperature, because we need high rate of production, and we are dealing with big size components, not small size components, right? Just look at this one. This will this diagram is basically two diagram is here. TTT diagram is here and CCT diagram is here. So can you people figure it out which one is TTT diagram and which one is CCT diagram here?
The dotted line is TTT diagram and
Very good.
complete solid line is CCT diagram.
Very good. Very good. Yes. So you can see this dotted line. Yes, this dotted line is this one. It is moving like this, and the other curve is this one. Right. So this dotted line is nothing but your TTT diagram, time temperature transformation curve. Right. Here it is MS, Martensite start temperature, and this is MF, Martensite finish temperature. You understand, this is the temperature axis in degree centigrade, and this is the time axis in seconds. So this is TT diagram. Anyways, so now you can see, and you understand, this is the transformation start temperature or transformation start curve, and this is the transformation finish curve or transformation finish time. This one. But you can see there is a solid line. Two solid lines are there. This is one solid, first solid line. This one up to this, and this is the other solid line this is up to this, and this is joined like this here. And this part is nothing but the nose of the C curve. This part is nothing but the nose of the C curve. So we can see what is the difference between TTT and CCT. It is clearly visible. Can you people figure it out? What is the difference here between TTT and CCT? CCT is the solid curve, this one, and TTT is the dotted curve. What is the difference? Just carefully look at the positions. That is the first difference. Carefully look at the positions.
Transformation temperature.
Transformation temperature, yes. Anything else?
A very slow cooling rate.
Slow cooling rate, okay. Just look at the position again, please. You will get it. Transformation temperature, okay, fine. Anything else? Time also. Time is also varying. So you can see the CCT curve is shifting downwards somewhat, and it is shifting towards right side also. Yes or no? Just carefully look at the diagram. It is okay? In comparison to TTT diagram, CCT diagram has shifted towards downward somewhat, and it is also shifted towards right side somewhat. So why it is shifting? Shifting means you understand. That means the rate of transformation is changing, right? So the rate of, or the kinetics of transformation, or the rate of transformation is somewhat different in CCT diagram as compared to TTT diagram, because of this continuous cooling, right? Because in TTT diagram we are cooling isothermally, but in CCT diagram we are cooling the steel continuously. So if we cool the steel continuously, and if you cool the steel in isothermal conditions at a constant temperature, then kinetics also changes, right? So this is the answer. So this is the first difference. So it is written is easily differentiate the TTT and CCT. So you can easily write the dotted line is showing TTT and the solid line is showing CCT. Then observation from CCT diagram, you can see observation is what? The observation is CCT diagram is shifted toward downward positions, and it also shifted towards right side positions as compared to TTT. Because this is because of change in kinetics of transformation or change in rate of transformation due to continuous cooling of the steel. Fine?
Sir,
Yes.
sir, we also do continuous cooling in TTT curve for martensite, forming of martensite and perlite. But there we don't see such kind of shifting of curve for kinetics.
Sorry, can you repeat again?
Sir, in TTT curve, during formation of martensite and perlite, we do continuous cooling, but we don't see
Do we do continuous cooling? We are not actually. Uh, we are not doing continuous cooling. TTT diagram is nothing but an isothermal transformation diagram. Isothermally, the confusion is what? Let me tell you. The confusion is what? You are getting confused. Okay, just look at this one. Okay, this one. Let's look at the TTT diagram, right? So see,
Yes, sir.
whether yes, this is the temperature, A1 temperature, right? And this is
Yes,
also
sir.
eutectoid steel. A1 temperature is nothing but your eutectoid temperature for eutectoid steel, right? Above eutectoid temperature, austenite is the stable phase, and below eutectoid temperature, austenite become unstable. Once it become unstable, it will transform into either perlite or either bainite or either martensite. It is okay,
Yes, sir.
right? And further, you can classify. It can form either coarse perlite or fine perlite. Similarly, for bainite, it may either form upper bainite or lower bainite, and martensite is fine, anyways. So you are saying that in TTT diagram, we are continuously cooling to get martensite. It is not true. We are not continuously cooling. We are ice cooling the sample isothermally. We are not continuously cooling actually. Similarly, for Bainite, we are also isothermally cooling. For perlite also we
So
are.
Bainite, that is Austin tempering is there, so that
That
is
is fine.
isothermal.
So
But
that
for
then you
martensite and
can say
pearlite,
yes, yes. Mm-hmm.
so martensite, sir, can you show the curve for martensite, that quenching curve of TTT? There is no such holding time
Okay,
is
yeah.
there.
No. Just look at this one. I'll start from here, and I will. Okay, do you remember how we generate this TTT diagram? That is the answer. How we generate TTT diagram? How you can draw? How you can plot a TTT diagram? Tell me. What kind of experiment do you have to do?
Heat treatment.
No. Just tell me the procedure. No. In the earlier class, I have told you the procedure. I remember. Who
Taking
can
the
answer?
sample to austenite
Yes.
temperature
Very
and
good.
then cooling it.
Then cooling it. That's all.
Yes, sir.
Okay. Who can tell me how to draw a TTT diagram? Suppose I
Sir,
will hand. Suppose I will give you a eutectoid steel, a big piece of eutectoid steel, right? Then how you'll draw a TTT diagram? Yes.
sir, first we have to take it to the oxidizing temperature, and after that, if we have to draw the TT diagram, first we have to take the sample to 600 degree, and there we have to keep it for some time and see when
600
the.
degree. 600 degree. Why 600 degree?
Sir, for different temperatures we have to do the experiment repeatedly.
So I will hand over you a steel, and you will take that steel to the austenitizing temperature. Then you bring it to the 600 degree centigrade. You are saying like that.
No, sir, we have to do the process repeatedly. Means first we have to.
Repeatedly. Do you think that that is the procedure? See, suppose you'll get a steel, big piece of steel. The first thing you have to do is you have to cut it into smaller pieces, right? You have to cut it into smaller pieces, like you want to do isothermal transformation. Isothermal transformation means you have to do transformation at a constant temperature. So you have to choose the temperature, at what temperature you want to do transformation. Suppose I want to do transformation at 100 degree, 200, 300, 400, 500, 600, 700. 1, 2, 3, 4, 5, 6, 7, for example. So I have to cut the steel into 7 pieces. The entire big piece of steel will be cut into 7 pieces, and that should be of uniform dimension. It is okay. That is the first procedure you have to do. Then second procedure is what? You take all the pieces of steel to the austenitizing temperature. Suppose you take the steel to the 800 degree centigrade, for example. That means above 723, you take it to 800, for example. Right? All the steel now is in a salt bath furnace, which is maintained at 800 degree centigrade. Right? You give a constant time also, holding time. Suppose you are giving 1 hour 1 hour holding time. So that means in all 7 pieces of steel, so that means all the 7 pieces of steel are now at 800 degrees centigrade and for 1 hour. So what is the microstructure in that steel? What will be the
Austenite.
microstructure? Austenite. So every 7 pieces of steel will be a homogeneous austenite phase now. Next stage will be what? You have to bring 1 piece of steel first, right? You take out 1 steel, you put it at 700 degrees centigrade. That means, suppose you have 7 number of salt bath furnace now. You can use 1 salt bath furnace. That is fine, no problem. But if you are like if you are very rich, then you can have a 7 salt bath furnace, and each salt bath furnace will be maintained at, like, 1 salt bath will be at 100 degree, and the salt bath will be at 200 degree, and the salt bath will be at 300, 400, 500, like that, up to 700. Fine. You take out one piece of steel from the 800 degree centigrade salt bath furnace and you put it at 700 degree centigrade. Similarly, you take out another piece of steel, you put it at 600 degree. You understand my point? Then you take out another piece of steel, you put it at 500 degree centigrade. Similarly, you have to put it into different salt bath at different temperature. Now you allow the steel to cool isothermally. So what you will get when you put the steel at 700 degree centigrade, then it will transform at this point and it will finish at this point. So you'll get a point here, you'll get a point here. Similarly, the steel piece which you have kept it at 600 degree centigrade, the transformation start at this point and end at this point. You'll get 1 point here and you'll get 1 point here. Similarly, the steel piece which is kept at 500 degree centigrade will transform at this point and end at this point. So you'll get a point here, you'll get a point here. Similarly, you'll get many points. Fine. For this temperature also you get this point and this point. For this temperature you'll get this point and this point. And suppose at 200 degree centigrade, you'll get a point here, right? You'll get a point here. Otherwise, you'll get a point here directly. Directly martensite will form at this point only, right? And for this steel, you'll also get a point here, right? Every time I'm doing isothermal cooling, I'm not doing any kind of continuous cooling, right? So that means even if I am doing isothermal cooling, I am getting perlite, I am getting bainite, and I am getting martensite. You understand my point? Suppose you are choosing a temperature of, for example, 250 or 260. You want to quench the, you want to cool the steel isothermally at 260 or 270. So this is my point. So I will get a point over here and I will get a point over here only. But I will not get any kind of martensite. But if I will choose a temperature of, suppose, 220, this temperature. So the moment I will keep the steel at 220, I will get a martensite within some seconds. Within some fraction of seconds, I will get martensite. It is okay? But that means it is not that 100% martensite will form. Listen it carefully. I will get martensite and austenite phase at this temperature. You are getting my point? Sivasis?
Yes, sir.
Suppose I will choose, listen it carefully. Suppose, what is the MF temperature here? What is the MF temperature here?
100.
Suppose 100 degree. Let it be 100 degree, right?
Yes, sir.
So if I will choose a temperature for isothermal cooling below 100 for this one, suppose 50 degree centigrade. So from 800 degree centigrade, I will take the steel to 50 degree centigrade. The salt bath temperature is suppose 50 degree, for example. So what will happen?
So the
Within fraction of
temperature
seconds,
will,
I will get martensite. Within fraction of second, I will get martensite. But what will that means? Within fraction of second, I will get 100% martensite. You understand now? There will be no austenite.
yes, sir. So,
So
but
this is actually isothermal. This is isothermal cooling. I am not doing continuous cooling.
sir, then what we do in continuous cooling, like if we are using salt bath, we continuously means decrease the temperature. We don't keep like here we kept the temperature at 100 degrees Celsius. So what would be the condition while doing this process in CCT?
Continuous cooling. Yeah, the confusion is continuous cooling means we are not using any kind of salt bath. But carefully look at it, we are not actually using salt bath. Salt bath, basically we can use a salt bath, that's fine. We can use a salt bath for continuous cooling also, but the temperature is not constant in the salt bath. It is okay now?
So, but for
Like, for
making
example,
martensite, so for making martensite, instead of using another salt bath, we can directly take out that to like normal room temperature condition.
you can take out the steel and
Yes,
you
sir.
can directly cool in the atmosphere.
Sir, then we can say it isothermal cooling. There will be a continuous cooling.
It is a continuous cooling, obviously. If you are
Yes, sir.
taking out the sample from the furnace and put it into the atmosphere, it is a continuous cooling. Obviously, it is a continuous cooling.
Yes, sir. It is a continuous cooling, and
Yes.
we can draw that in TTT curve.
Yeah, you can superimpose the cooling curve. You have to draw a cooling curve. That's all. to show that, you have to draw a cooling curve. Suppose my temperature is here, I will draw a cooling curve like this, or this, anything. It
Yes, sir.
depends upon the
For this,
cooling.
yes, sir. For this exact thing, we can draw a quenching line on this TTT curve.
It depends. If you are continuously cooling at a very fast rate, you can draw like this only simply. You can draw a cooling curve depending upon your situation. If you want to do at a very fast rate of cooling, the cooling curve will be like this. The cooling curve will be like this. It will be not like this, or
Yes,
it will
sir.
be not like this.
So
Yes.
all of these cooling curves are continuous. Like there is no such point there where you can see a slope will be 0. Like no holding time in between the curve. So that shows that all these are continuous cooling curves. So why there is no shift of this C?
Why there will be no shift of C?
Yes, sir.
This.
That's C curve.
See,
Yes, sir.
can you tell me this? What is this curve is showing actually? This curve is showing what exactly?
Perlite start
No,
temperature.
who told this is perlite start temperature? This is perlite start temperature.
So perlite and bainite.
Yes,
So
obviously. This is,
transformation, sir. Yes,
yeah,
sir.
this is
Transformation
transformation start
started.
temperature. It may be
Yes, sir.
if this is the reason, if this is the bay, the perlite will form. If this is the bay, bainite will form. That's all. It is okay.
Yes, sir.
And similarly, this line will show you Martensite start formation. This is a
Yes, sir.
continuous line, right? This is a continuous line. The first line is continuous actually. The second line is not continuous. It is dotted one here, right? If it is matching here, it may be a continuous again. Anyways, so this line is showing you the transformation start temperature. Transformation start temperature means at that temperature, particular temperature, the transformation will start, and it also showing the time. It is not only the temperature. This is the time also, right? At suppose this is the temperature here. So this point is showing the transformation start temperature and transformation start time. Both things are here. It is okay? You understand?
Yes, sir.
Both things are here. Temperature is here and time is here. Similarly, for continuous cooling also, you will be having temperature and time. Listen it carefully. Both things are here, right? But difference is what? In Ttt diagram, we are holding the steel at a constant temperature, and we are trying to find out at what temperature at what time the transformation will start. That is why Ttt diagram is defining the kinetics of transformation. It is okay for a particular constant temperature. But in CCT, just look at this one. Let's look at this one. Yes. Look at this one. Here also we have temperature. Here also we have time. But we are continuously cooling actually. We are see, whenever we are continuously cooling, suppose we are continuously cooling a steel, and in the another case we are cooling the steel at a constant temperature. So kinetics also changes. Kinetics is not fixed. The start temperature and finish temperature, or the basically start time. Kinetics means start time. I am talking about the time, rate of transformation with respect to time. Yes. So start time and finish time will change. If you are doing continuously cooling and if you are doing isothermal cooling, the time of transformation changes actually. That means it is saying, it is what it is saying. Basically, it is saying that if you are doing transformation at constant temperature, transformation will start earlier and finish earlier. It is okay. But if you are doing continuously cooling, the transformation will start, it will delay, and it finish will also delay. It is okay now? It is
Sir,
okay.
if the kinetics different, then the procedure must be different.
Procedure means what kind of procedure you are talking about? Procedure means, yeah, obviously procedure means just you have to take out the steel from the furnace and you have to cool it in the air or in the any medium or anything. But cooling should be continuous. It should not be stopped. the temperature of the medium, suppose air temperature of the air is the sample temperature should vary, right? It should not be fixed.
Hello, sir.
Yes.
If we take out the sample from the salt bath and keep it in the normal temperature or the room temperature, the final temperature is the room temperature, which is constant. So it should be an isothermal. Why it is a constant?
No. You people are getting confused. See, what is the need of using salt bath? The need of using salt bath is salt bath have a constant temperature with time also. Suppose you start with 0 time and you end with suppose in 1 hour, for example. Time is 0, then finish time is 1 hour. So in entire 0 time to 1 hour, the salt bath temperature will be constant. You are getting my point? That means the sample temperature will also not change. It is okay now?
Sir,
Suppose
sir, if the sample is at 800 and the salt bath temperature is 300, and if we put that sample in the salt bath, the ambient temperature of the salt bath is 300, so the ambient temperature of the sample will be 300. But the sample itself will cool down from 800 to 300.
okay, you are talking about that part. See, this experiment will be done at a very fast rate. People are getting confused. I am not giving sufficient time. Suppose, listen it carefully. To draw a Ttt diagram, you need two salt bath furnace, for example. You are having 2 salt bath furnace. One salt bath furnace is suppose maintained at 800 degrees centigrade, and the salt bath furnace is maintained at suppose 300 degrees centigrade, as you talked about, right? So that means you put the sample you put the steel in 800 degrees centigrade in the salt bath furnace. You make it austenized, homogeneous austenite. Then suddenly, quickly, you have to take out the sample and you have to put it into the second salt bath furnace, which is maintained at 300 degrees centigrade. I am not giving sufficient time for cooling. It is okay. It is not like that slowly I will take out the sample from the 800 degrees centigrade. I will stop for some time. Then I will put it into the next salt bath. It is not, I'm not doing like that. I'm suddenly taking out the sample from the first salt bath, and beside the second salt bath will be there. I will put it. It is like a quenching, you can say. It's like
Yes,
a sudden
sir.
cooling.
Yes, sir. In the second salt bath, the steel sample will cool down from 800 to the lower temperature.
Yes, obviously 300.
Yes, sir. And as the temperature of the salt bath is constant, the second salt bath. That's why we are saying it as a isothermal cooling.
Yes, obviously.
Then, sir, in case of quenching, the room temperature is also constant with time. We can say that a salt bath at 25 degrees centigrade. Then why?
Yeah, the point. I understand your point. I understand your point. What is the problem here? Yes. Suppose you are taking out the sample from 800 degrees centigrade, you are putting it into the air, and you are saying it is also an isothermal cooling.
Yes, sir.
Right? But
Yes, sir.
you can call that as an isothermal cooling, right? But the cooling will be very slow. You are getting my point. The sample temperature will change slowly. The sample temperature from 800 degrees centigrade to 100 degrees centigrade, or room temperature, for example, 25 degrees centigrade, it will cool very slowly. You are getting my point. It will take some time. It will take some time to reach 25 degrees centigrade from 800 degrees centigrade. But if you are using a salt bath furnace and you are doing very rapid quenching, it will not take much time. Suddenly from 800 degrees centigrade, within fraction of second, it will reach 300 degrees centigrade. It is okay? You understand my point?
Yes, sir. But how the salt bath makes it possible means very rapid cooling with the atmosphere back.
You do not understand my point. My point is, see, salt bath is a bath which will maintain a constant temperature throughout the time. That is the role of the salt bath only. The salt bath temperature will not change. The salt bath temperature, suppose salt bath temperature is 500 degrees centigrade. You can take 100 hours, 200 hours, the salt bath temperature will be 500 degrees centigrade. It doesn't, the temperature will be not affected by the sample temperature. It will maintain a constant temperature throughout the process, right? So you take out a piece of steel quickly. Quickly means you are not taking, giving any time. You are taking a piece of steel, you are putting it at 100 degrees centigrade, and from 800 degrees centigrade. From 800 degrees centigrade, you are taking out the sample and you are putting it at a temperature in the salt bath maintained at 500 degrees centigrade. So within fraction of seconds, you are taking out the sample from the 800 degrees centigrade and you are putting it into the 500 degrees centigrade salt bath furnace. So I am not giving any time. In this time is very less. But when the sample is put at 800 degrees centigrade, I am giving it sufficient time to do isothermal cooling. You understand my point? Isothermal cooling will happen inside the salt bath. That is the point. You are giving sufficient time. But in case of air, you are getting my point. In case of air is a what? Air is not fixed. Am I? You are getting my point. Air is not fixed. Air is always in the motion, right? So suppose fresh air is coming in contact with the sample first, then fresh air will become heat and it will remove from the surface. New air will come. You are getting my point. Hello.
Yes, sir.
Every time new air is coming in contact with the sample. But in case of salt bath, every time the same salt bath will come in contact with the sample. You are getting my point right now?
Sir, in that case, it will be called adiabatic. Why we get telling it isothermal if it is not lost?
No. Adiabatic means what? Constant heat will be there, right? But
Yes,
isothermal here means we are giving time also, no? That means from the high temperature to the low temperature cooling, you are giving time also. You are giving this, you just look at the time period, right? This time period are in seconds. Yes or no? These time periods are in seconds. That means I am not actually giving it some hour or like 20 hours, 30 hours. That is not the thing. The transformation will start quickly at certain time, right? And within some seconds, it also, but it also depends upon the cross-sectional area. I told you. Suppose you are taking a very thin piece of steel, You austenitize it and you put it into the salt bath. Within some seconds, the transformation will finish. Within some seconds, the transformation will be finished because the thickness of the sample is very low. But for industrial scale, the thickness of the specimen is very big. Very big dimension we are dealing with, right? It will take some hour or it will take some minutes. You can say not hours, it will take some minutes, for example. Not second, right? So isothermal cooling means we try to keep the sample at a constant temperature and we'll see at what time the transformation will start and at what time the transformation will finish. Transformation start means suppose austenite to pearlite transformation. So pearlite will start transforming from the austenite, and when all the austenite will become pearlite. That is our criteria actually, right? But in the another case, continuous cooling means in continuous cooling also austenite may convert it into pearlite. That is also fine. That is also okay. Even if you are doing continuous cooling, the transformation will happen like austenite to pearlite transformation. And there will be a transformation start time, there will be a transformation finish time. But the kinetics will change, right? Because you understand, because in isothermal cooling, we are trying to maintain a constant temperature always, right? That means you can, in other words, you can say the surface temperature and the core temperature is fixed. But in continuous cooling, it is not so. The surface temperature and the core temperature will be not fixed during the continuous cooling, because the surface will cool at a very fast rate, but the core will not cool at a fast rate. It will cool slowly. But in isothermal cooling, you can understand everywhere in the sample, the temperature is fixed. At the surface temperature and the core temperature is fixed. You understand my point now? Is it okay?
Sir, if there is such a problem, then why we use CCT in industry if we are handling big samples with big diameter, or like there will be some retained austenite or
See,
something in the core?
to get a transformation, many things are there. It is not like the dimension only. Okay, how many of you remember what affects the transformation? Already we have discussed a lot of things. What affect the transformation? Apart from the dimension, forget about the dimension.
Alloying elements.
Obviously, the composition is very important. It is plain carbon steel or it is alloy steel. And if it is a plain carbon steel, then it is either low carbon steel, medium carbon, or high carbon. Since again, another point is if it is an alloy steel, it is a low alloy steel or high alloy steel. Or if it is alloy steel, what kind of alloying element is present? Ferrite stabilizer or austenite stabilizer? Lot of things we have already discussed. So why you are getting confused? Transformation do not depend upon only thickness of the sample. It also depend upon the composition. Composition matters. Whether we are dealing with eutectoid steel or hypoeutectoid or hypereutectoid, or whether we are dealing with plain carbon steel or alloy steels. Suppose cobalt is there. So what will happen? Who can answer? If a steel contain only cobalt, what will happen to the transformation?
There will
Sir,
be
the
no.
carbon stick to
The
left.
TTT will not shift.
Can you repeat?
The TTT, the seeker will not shift.
Yes, it will not. Don't tell me those things. What will happen to the transformation? Just tell me. What will happen to the rate of transformation?
Remain the same.
Okay, if I have a lot of chromium in my steel, what will happen to the rate of transformation?
Decrease.
Yes, it will be delayed, right? It will be delayed, right? That means austenite is still
Yes,
stable.
sir.
Austenite will not decompose easily. Because why it will not decompose? Who can answer? Let me see. If chromium will be there, why austenite will not decompose quickly? Or why the finishing of transformation will not happen quickly? Why it will be getting delayed? In the previous lecture, we have already discussed.
Austenite stabilizer.
Chromium is a austenite stabilizer? What you are saying? Chromium a austenite stabilizer?
No, no, sir.
So you are saying chromium is a austenite stabilizer? Who can answer? Rutubarna, can you answer this one? If you have a chromium in your steel, suppose you have a steel only containing chromium as an alloying element. So why the transformation will be delayed? Rutubarna?
Sir, chromium is a ferritic stabilizer, so
Yes.
it will unstabilize the austenite.
So if austenite will be unstabilized, then transformation will be faster. Now, why it will be delayed? That is my
Sir,
question.
the nose of the seeker will shift rightwards.
Oh God, why don't tell me those things. Nose of the seeker will shifting right side means austenite is still stable. It is not getting unstable quickly. It is taking some time to become, or it is taking some time to get transformed into other products. Or the finishing line will also shifting towards right. But why it will shift? That is the question now.
So
Who can
formation
answer?
of chromium carbide.
Very good. The formation of chromium carbide. Very good. So what will happen if chromium carbide will be there?
So they like go near to the grain boundaries.
Don't tell me about grain boundaries. There is nothing relationship with the grain boundaries and the rate of transformation. In the previous class, I have told you already. Yes. Samrat.
Solubility will take more time, sir.
What?
Solubility will take more time.
Solubility. Okay, fine. Solubility. But how you can relate with the diffusion? Tell me just.
So diffusion decreases as a lot of carbon goes into the precipitate form with chromium.
Okay, how many of you remember? Suppose you want pearlitic transformation. In another case, you want bainitic transformation. And lot of alloying elements are present. Lot of carbide forming alloying elements are present. So in which case the transformation will be more delayed? Shall I repeat the question? Basically, in pearlitic transformation, it will be delayed. Why? Because pearlitic transformation involves diffusion of carbon atoms and iron atoms. And if other alloying elements are also present, they all will diffuse, right? But in case of bainitic transformation, what will happen? Only carbon atom will diffuse, and that is only during the nucleation stage. So more effect will be on the pearlitic transformation. So pearlitic transformation will be more delayed. It is okay? But similarly, the same thing, if you have ferrite stabilizer, even then the transformation will be delayed. Why? Because some ferritic stabilizers are more strong carbide former, right? So if strong carbide former will be there, that means carbon is present in the carbides, alloy carbide in form of alloy carbides. So the diffusion of carbon atom will be retarded. There will be retardation of the diffusion of carbon. You want transformation to happen, so you need diffusion, but diffusion is getting slow down. Why? Because some of the carbon is present in form of carbides, alloy carbides, and they are strong carbides. You people are getting my point, or shall I repeat? Shall I repeat in easy words?
Yes, sir.
You want transformation to happen, right? If you want transformation to happen, then you need diffusion to happen, obviously. If there will be no diffusion, there will be no transformation. Basically, I'm talking about perlite, for example. I'm not talking about martensite or bainitic transformations. Or it may be bainitic transformation because it also involves diffusion of carbon in the nucleation stage only. So suppose you want transformation to happen in case of perlitic transformation, you need diffusion to happen. And if diffusion will be faster, then transformation will be faster. If diffusion will be slower, then transformation will be slower. It is okay? Up to this, you people understood? Up to this, it is fine.
Yes, sir.
But if carbon atom will be present in form of alloy carbide, then what will happen to the diffusion? It will be slow or fast?
Slow.
Slow.
Obviously slow, because carbide is not free now. Carbon is not in the free state. It is in the combined state, and again it is in the stable combined state. Alloy carbides are more stable as compared to that of cementite. So now suppose, okay, fine. Suppose you have two steel. In one steel you have cementite. In another steel you have a stable alloy carbide. So diffusion will be faster in which case? Diffusion of carbon will be faster in which case?
Cementite.
Obviously cementite. Why cementite?
Because that is less stable.
Because cementite is a weak carbide as compared to that of alloy carbides, strong alloy carbides, right? Or you can, in other words, I can say cementite will be easily soluble in the austenite phase, but alloy carbide will not easily soluble. Transformation means two kind of transformation: room temperature transformation to high temperature transformation, or high temperature transformation to room temperature transformation. Both are important, actually. Now it is clear to everybody. Okay, let me show you this part. You'll get, it will be clear, more clear. Huh? Okay, what is this diagram is showing? What is this diagram?
Mart tempering.
Yeah, this is Mart tempering. So what is the need of holding here? Why you are holding the sample here first? I'm quenching my sample to this region, then I'm holding here, then I'm cooling it again. What is the need of holding here? The figure is showing. Just look at this diagram carefully. Already this has been discussed. Sibasis and Soumya, your doubt will be clear in this part. You are getting confused in the continuous cooling and isothermal cooling. Who remember why we have hold our sample in this condition at this point?
Sir,
For
to
the
get
surface.
same temperature from the surface to the floor.
Very good. To get the same temperature to the surface and the what? To the core part or the center part, right? So this can be done. Can you, do you think this will be done with the help of air? Can you do that?
No, sir.
So what do you need?
Salt bath.
Salt bath furnace. Now I think your doubt is clear.
Yes, sir.
These
So,
things can be
this one,
possible. Yes.
so
What?
but this one is a heat treatment process. But like if you want to make for
That
this
is
smart
also a
temperature,
heat treatment. If you want to draw a Ttt diagram, whether you want to draw a Cct diagram, you need a heat treatment. That is also
okay.
we are doing heat treating. We are
Yes, sir.
austenitizing the sample. We are cooling the sample. Either we are cooling the sample continuously or we are cooling the sample in isothermal way.
Yes, sir. So, but if I am making martensite, there are two cases. I can make either with the help of salt bath or in
Yes.
uh,
Yes.
like room temperature.
Or continuous cooling to the room temperature. Yes.
Yes, sir. So then the graph of the continuous cooling which I have done at room temperature, I can mark that under the CCT, whereas I have to mark this salt bath case under the TTT.
Sorry. This part I am not getting. What you are saying? The
Yes, sir.
last part. Can you
So,
repeat?
yes, sir. So there are two samples with me, two martensites.
Okay, fine.
One which by using the help of
Salt
that.
bath with the help of
Yes, sir.
atmosphere. Yes, I understand. Yes.
Yes, sir.
Hmm.
Sir, then I have to mark this continuous cooling like I have done, which one I have done under means it at room temperature condition under CCT. But
Okay.
whereas I have to mark this salt bath product martensite under TTT.
Yes, I understand your point. Yes.
So, so is this the case? Like, am I correct?
Yes, obviously.
Okay.
That is the answer. Obviously, right.
Okay, sir. And
So that's what is the need of showing this TT diagram? If you want to draw a CCT diagram, you do not have to show this TT diagram. I have drawn this one to distinguish them. That's all. You should not get confused. You can erase all this dotted line. You can draw this line only. Only this solid line can be drawn. This two diagram, this two curve I have drawn to just explain you the difference. That's all. To distinguish the TTT and CCT, both these things are. You should not confuse between these lines and this top line to this line. These lines should not be confused with this TTT and CCT. These lines are only the cooling curves. These lines are nothing but the cooling curves. Cooling curves means at how much time, that means it is showing the change in temperature with time. That's all. And these curves are nothing but the start temperature and finish temperature. It is okay now? Transformation start temperature and transformation finish temperature, this curve will show. But these curves will show you the cooling rate. At what time, what is the temperature? At what time, what is the temperature? That's all. So cooling curve should not be confused with the TTT and CCT. Now your confusions are clear, I think, up to this. Sibasis, your confusion are clear or still
yes,
you have
sir.
any confusion? Soumya?
Yes, sir.
So so I think you people have missed these classes, earlier classes, I think. Austempering and Martempering.
No, sir.
But then why you have any confusion? See, this things is done with the help of salt bath. If you are not using any salt bath and you try to hold it at this temperature with the help of air, then what will happen? It will cool automatically to the room temperature slowly. You understand my point? But if you are using a salt bath, you can hold the sample at this temperature for many hours if you want. 10 hours, 20 hours, 30 hours, depending upon the situation. It is okay?
Yes, sir.
Because air is not fixed. Air is always moving. Suppose you take out a sample from the high temperature and you put it into the normal atmosphere. What will happen? The air surrounding the sample will get heated up and it will remove. Then new air will come in contact with the sample and again it will remove. So every time new air is coming in contact with that. It is not a constant temperature. But if you are using a salt bath, every time same constant salt bath will come in contact with the sample. Every time the temperature will be fixed. Now it is okay. So can you people tell me, if you are using a salt bath, the temperature, it is a isothermal cooling or continuous cooling?
Isothermal.
Similarly, if you are using air, normal air, then it is a isothermal cooling or continuous cooling?
Continuous cooling.
So now it is clear?
Yes, sir.
Yes. Okay. Yeah, you can ask me, no problem. No need to scared about asking doubts. Huh? You can ask me anytime. The confusion should be cleared actually. So you can easily distinguish between CCT and TTT, right? So there is a shifting of this CCT curve towards downward and towards rightward because transformation start temperature and transformation finish temperature is changing because the kinetics is changing due to change in the cooling conditions. Because earlier condition was isothermal cooling, next condition was continuous cooling. So if there is a change in cooling conditions, obviously the kinetics will change. That's all. Next one is observation is clear. You can write it. Then yes. Another observation. Can you people tell me any other observations in the TTT and CCT?
Increase in incubation period.
That's fine. That already I've told you. This shifting part. Don't tell me those things. That is already I told you that is shifting part now.
TTT is continuous till low temperature, but CCT is not.
Sorry, can you repeat again?
So towards the lower temperature, TTT curve is there, but CCT is not.
Okay, yeah, yes, very good observation. So you can see TTT diagram is a continuous diagram up to this and this, but CCT diagram is up to this only. Or in other word, I can say CCT diagram is drawn up to the nose. Below the nose, we are not showing any curve of the CCT diagram. So CCT diagram is drawn up to the nose of the curve, C curve. Right? Below the nose of the C curve, CCT diagram is absent. It is okay to everybody? So can you people tell me why this is happening? The name is saying CCT. Can you people tell me why we are not drawing the CCT curve below the nose of the C curve? But TTT diagram we are showing below the nose of the C curve also.
Sir, then there will be two temperatures at a constant time.
Two temperature. Sorry, I don't understand what you're saying. Two temperature at constant.
Sir,
My
if we
question was why we are not drawing the CCT curve below the nose of the C curve. It is only up to the nose. Below the nose of the C curve, it is not there. It is absent completely. But in case of TTT, you can see it is a continuous diagram. It is showing the C curve. It is showing the nose of the C curve, and below the nose of C curve, it is also there. The curve is also present after the nose of the C curve.
Bainite is not there.
That means Bainite is not there. Very good. Why Bainite is absent? In which case Bainite is absent here?
CCT.
CCT. Why?
Because we need ostempering for constant holding time is there for Bainite formation.
Don't tell me off tempering and all. To tell me the reason why Bainite is absent in CCT.
Sir, to make bainite, we can do by using constant cooling. We have to. There is a holding time is there for bainite. So which
Asutosh
is
Sahu, can you answer? Asutosh Sahu. Asutosh Sahu. Asutosh Sahu. Okay, Asutosh Sahu is absent. Chandan Maharana, can you answer this one?
Yes, sir.
Can you answer this one? Answer the question.
Sir, because there is no soaking time.
There is no
Soaking time.
soaking time. Can you simplify that? What do you mean to say?
Sir, in continuous cooling, there is no transformation. At different because that here the temperature is vary.
Okay, temperature is varying.
But in triple T, there is some constant temperature like critical temperature at where we get the transformation.
Okay, fine. Ipsitas, how can you answer this one?
No, sir.
Okay, Latmika,
Yes, sir.
can you answer this one? Why in CCT curve it is the curve is absent below the nose of the C curve? It is up to the nose.
So no, sir.
Okay, Mohammed. Mohammed. Mohammed, you are absent. Amrita, can you answer?
No, sir.
Okay, up below this one, below the nose of the curve, what are the different phases present? What are the different phases present below the nose of the C curve? Below the nose of the C curve of the TTT diagram, what are the phases present?
bainite and martensite.
Bainite and Martensite, very good, right? But Martensite basically forms if you do continuous cooling. We also know that, and you can do also isothermal cooling, no problem, right? So Martensite will be still there. It is okay. In CCT diagram, you can also show Martensite start temperature and finish temperature, right? That means something is absent. What is absent here?
Bainite.
Bainite is absent. Very good. Because now the question is why bainite is absent in the CCT diagram. Because it is a continuous cooling diagram. And we remember bainite basically forms on isothermal cooling. At the bainitic range, if we are cooling the sample from the austenitizing temperature at the bainitic transformation temperature by isothermal cooling, then bainite will form. Otherwise, bainite will never form. So bainite basically forms by isothermal cooling of the steel sample at the bainitic range. What is the bainitic range? Who remember? What is the bainitic range temperature? If you want to form bainite, what is the temperature range?
So 200 to 400.
200, not 200. Basically depend upon the composition, you can say, but basically you say it is depending upon the composition, but it's basically from 540 or 550, basically 540 to 550 to below 240, like that, or 230. 540 to 240 or 230, this is the range. Upper bainitic range is from 540 to like 300, you can take. And lower bainitic is 300 to, for example, 240, like that. Anyways, so you understand. So another difference between the CCT and TT is Cct diagram is up to the nose of the C curve, but Ttt diagram is complete. Fine. And this is because in continuous cooling transformation, we are continuously cooling the steel sample from the austenitizing temperature. So Bainite formation is not possible. So that's why this curve is up to this. But by continuous cooling, we can form martensite also. So martensite start temperature, martensite finish temperature is present. It is okay? Can you write it down in your examination, and can you answer this question in interviews confidently? Recently, these questions have been asked in the interviews of Vedanta. You can contact your seniors if you want. Okay, this part is clear. Shall I write it down, or you can write it? Okay, you can write it down. Huh? So an addition of manganese into steel leads to formation of two bays, upper and lower bays. So this is very interesting again. Just look at this one. If you remember, in the previous class, we have discussed about the 4 types of Ttt diagram possible in case of alloy steels. In one case, that is, the diagram is completely similar to the plain carbon steel. And in second case, we have seen we have 2 bays. Both bays are present, perlitic bay and bainitic bay. In another Ttt curve, we have seen only perlitic bay is present, bainitic bay is absent. In another, we have seen we have only bainitic bay, but perlitic bay is absent, right? So that means this kind of diagram is possible when we have alloying elements, right? We have perlitic bay, we have bainitic bay, and we have martensite. Right below this one, that means we have martensite only. So this diagram is possible when we are dealing with alloy steels, right? So that means addition of alloying element leads to formation of 2 bays, perlitic bay and bainitic bay. It separate, or you can say it separate the TTT or Ttt diagram into 2 bays, perlitic bay and bainitic bay. So this is possible by addition of manganese, right? So if you add only 2% manganese into the steel also, then the Ttt diagram will be becoming 2 bays. One is perlitic bay, upper bay, and bainitic bay, lower bay. So if this is the situation, can you people think of it? If you are adding an alloying element and the Ttt diagram is becoming converted into 2 bays, one is perlitic bay and bainitic bay, what kind of significance you will get in case of Cct? Suppose you are continuously cooling the steel, what will happen? Can you tell me? Suppose the start temperature is here, you are continuously cooling the sample. You are continuously
We will
cooling.
get only perlitic bay.
Listen my question carefully. Suppose I am giving you a steel, containing 2% manganese, right? And you draw a Ttt diagram, right? And in that Ttt diagram, you are getting that now my Ttt diagram is not continuous. It is divided into 2 bays. One bay is perlitic bay, that is upper bay, and another bay is the bainitic bay, that is the lower bay, right? Now you have same steel. Now you take the steel to the austenitizing temperature. Then you cool the steel continuously in a different cooling rates, but the cooling is continuous, right? What you will get? Suppose the cooling rate is like this. The cooling rate is like this. What advantage you are getting? Can you tell me? Continuously cooling. You are doing continuously cooling at different rates. What advantage you will get? Just compare this one with this one.
Sir, we can get bainite also in some cases.
Very good. We can get bainite. Why we can get bainite? Can you justify?
Bainite is present there.
Yes, because bainitic bay
2
is
bays,
present clearly.
perlitic and
There is a
bainitic bays.
clear presence of bainitic bay. That means if you are cooling at this rate, look at the crusher. If you are cooling at this rate continuously, even if it is continuous, that means I am going into the bainitic region. So I can form a bainite by doing continuous cooling.
Sir, is there any reason behind
The
it?
reason behind is the presence of alloying element. That is the assignment I have given you in the previous lecture. there are certain alloying elements, for example, manganese, as I told. There are certain alloying elements which divides the continuous C curve into two C curves. That means one is the perlitic bay, another one is the bainitic bay. If bainitic bay is clearly present in the Ttt diagram, then just by doing continuous cooling, you can get a bainite. Because you can see the zone is up to this much, perlitic bay is up to this much, right? If you want perlite, then you have to do very, very slow cooling. You understand my point? If you want bainite, you have to do somewhat intermediate cooling and you reach the bainitic region. That means here perlite is absent, here bainite is present. So to get a bainite, the perlitic bay is absent up to this much, you can cool up to this much also, you will get a bainite. So this is the effect of alloying element again. So that means in another word, I can say there are certain alloying elements like manganese, if they are present, they form two bays, bainitic bays and perlitic bays. And if we are doing continuous cooling also from the austenitizing temperature, if we miss the perlitic bay, we maximum chance that we will get a bainite in the structure. But suppose I am cooling my sample in this range. So shall I get a bainite? Yes or no? If my cooling rate is this much, shall I get a bainite?
No.
No.
No, sir.
Because cooling rate is somewhat higher. So I will end up with martensite only. I think the concept is clear. So I have written over here also. Addition of manganese into the steel leads to formation of two bays, upper and lower bay. What is the conclusion? The conclusion you can write is we can get also bainitic microstructure by doing continuous cooling. But if it is only carbon steel, can I get a bainite by doing continuous cooling? What is the answer?
No, sir.
If I have a plain carbon steel, it may be medium or high carbon or anything. Can I get a bainitic microstructure by doing continuous cooling?
No, sir.
No, sir.
Why no? What is the answer? Why no? Can you justify? Because we do not have two bay. Because two bays are absent. Perlitic bay and bainitic bay are not present. It is a continuous curve now. Only we need to do isothermal cooling. Then only I can get a bainite. If there is a question in your examination, suppose you have a steel containing manganese and there is a steel containing only carbon, right? So how to get bainite in a steel containing manganese and how to get bainite in case of plain carbon steel? So what is the answer? What you can write? Shall I repeat the question?
We can do continuous cooling in case of manganese steel, but we can get bainite in the carbon steel.
So we have to hold it around the bainitic region to get bainitic bainite in only carbon steel, but in manganese, in steel containing manganese, we can achieve it by continuous cooling.
Your both answers are partially correct. Can you try it again? Just use your mind. Something is missing. You have missed something. Your answer is correct. No, it is not wrong, but still you have to add something. I'm not asking about the explanation. I'm asking just only the answer. Can anybody want to try?
So in case of plain carbon steel, we can do isothermal cooling.
Very good, to get bainite. What about steel containing manganese?
So in steel containing manganese, we can do isothermal cooling or continuous
Very
cooling.
good, very good, very good, excellent. So if you are having a manganese steel, suppose 2% manganese or 3% manganese, here you can do two things. Either you can do continuous cooling to get bainite, or you can do isothermal cooling to get bainite, right? That means you can do, this is the image, final image. It is written over here. 2% manganese steel cooling curve superimposed on Ttt diagram, right? So that you can see the Ttt diagram has divided into two curves. One is the upper curve and one is the below curve. Upper C curve and below C curve. Upper C curve is for perlitic bay. Bottom C curve is for bainitic bay. So just by doing continuous cooling, this is a continuous cooling curve. If you go through this, you will get a bainite. you can do another thing. You can quench it up to this point, then you hold it isothermally. Again, you will get bainite. Two things can be done. But continuous cooling curve should be also known one. If you are doing continuously cooling like this, you will not get bainite, you will get perlite. If you are continuously cooling like this, you will not get bainite, you will get martensite. So continuous cooling should be also in a moderate range. You have to find it out by help of research papers. You should have a prior idea at least. So up to this, it is clear. Now we'll move to the next topic. Very important topic. Very important for exam point of view and for your interview purpose and for your GATE examination also. Concept of hardenability. Hardenability is a very important characteristics of a steel. Like hardness is a very important characteristics. So hardenability is also very important. So now to explain the hardenability concept, let me give you a situation first. Just imagine, this is a situation. What happened to the microstructure when a reasonably large cross section or dimension steel is austenitized and rapidly quenched? This is the question. Can anybody think of it? Just read the question and tell me the answer. Let me see who can answer it quickly.
Sir, in this case, we can't get 100% martensite because the cross section is so large.
Okay, very good, very good. Anybody want to try this one? Pranav have tried well. Can anybody want to try, and can anybody want to elaborate this one? See, suppose you have a piece of steel which is having a very large thickness, or it is having a large dimension, very bigger piece of steel you have, right? You take that steel to the austenitizing temperature, you make it homogeneous austenite, then you quench it. So upon quenching, we understand we'll get martensitic microstructure, right? But we will not get martensitic microstructure throughout the cross section. Throughout the cross section means from the surface to the core or from the surface to the center, maximum chance that you will not get 100% martensite. Why this is so? This is so because the rate of cooling is different at different cross section. The cooling rate is higher at the surface, but cooling rate will be minimum at the core or the center of the steel piece. Why? Because this is a large cross section piece of steel, or the steel piece is of having larger thickness, right? Because the surface is easily come in contact with the atmosphere, it will cool easily. It will cool at a very fast rate. The faster rate of cooling will give rise to martensite. But the center part of the steel piece or the core of the steel piece is even at a high temperature. It will cool slowly. The cooling rate is very slow at the center and at the core. So what will happen? Some transformation has happened. Some diffusion based transformation will be possible at the core. So perlite will form at the core, and at the surface martensite will form. Maximum chance is that it will form finer perlite at the core or at the center of the piece of steel, but at the surface you can get martensite. Up to this it is okay, or shall I repeat? Do you people want me to write here?
Sir, your screen is not visible.
My screen is not visible?
Yes, sir.
Okay, just wait. Let me check. Okay, you people have understood if you have a bigger piece of steel or bigger thickness of steel piece and you austenitize it and you quench it, what is the microstructure you will get? Shall I write? Shall you want me to write, or you have understood? Okay, I assume that you people have understood. I will not write. So what happened to the hardness value at different cross section of the same steel? Can you people tell me what happened to the hardness value then? What happened to the hardness value? After doing this, what happened to the hardness? The hardness value will change, right? It is a variable hardness. The hardness at the surface will be different to that of hardness at the core or at the center. Why? Because of different microstructure, right? Surface is having martensite, so it will be having maximum hardness value. But if you slowly go down to the center, the hardness will decrease and it will be minimum at the center or at the core. Now, due to these things, the hardenability concept is coming into the picture. So what is hardenability? So in simple way, I can say hardenability means susceptibility of steel to get hardened. Hardenability means susceptibility of a steel to get hardened, open, or on quenching. The steel will become hardened, right? It will become stronger and harder, right? Upon quenching. That means how easily the steel is becoming harder upon quenching. That is called hardenability. Susceptibility of a steel to get hardened on quenching. So in other words, it can be also explained like this. It defines the depth and distribution of hardness across a cross section or along the cross section. It defines the depth and distribution of hardness across a cross section. That means it is saying at different depth of the piece of steel, what is the value of hardness. Like at the surface, it is harder, and at the core, it is softer. Right? This is all about hardenability. It also can be defined ability of a steel to get hardened. Ability of a steel to get hardened. How? By forming martensite. So hardenability is nothing but the ability of a steel to get hardened by forming martensite. How? Throughout the cross section of the steel, of the sample or the specimen, throughout the cross section of the steel, open, without drastic quenching. So this part can be justified. Okay, can you people tell me one thing? Already, I think we have discussed that in IPM part also, and earlier part also. Suppose you have two pieces of steel. In one steel one steel is carbon steel, and the steel is your high alloy steel, right? So in which case martensite form will be easier. In which case the martensite formation will be easier. Am I audible to everyone? Am I audible to everyone?
Yes, sir.
Yes, sir.
Yeah. So you have two pieces of steel. One is carbon steel and the piece is alloy steel, high alloy steel. So in which case martensite formation will be easy. Okay, what happens to the nose of the C curve when there is an alloying element? A lot of alloying element is there. What happens to the nose of the C curve of the Ttt diagram when there is lot of alloying element are present in the steel?
Sir, it shifts towards right.
It shifts towards right. Yes, very good. You understand the point. Already we have discussed that in the earlier class and today's class. So if the nose of the C curve moves towards right, so if you cool the piece of steel at a very slow rate also, can we form a martensite? Open
Yes,
slow
sir.
cooling. Yes. How? Yes. Can you justify that, Soumya?
सर कोटा राइट साइड शिफ्ट हो जाइए तो स्लो रेट रे कूलिंग करले भी तळे मार्टेनसाइट ही फॉर्म हो.
No. Justify. Just justify that.
The transformation will not start because the
No. Which kind of transformation will not start?
diffusion based.
Yes, diffusion based. So that means you are getting how you can explain. You can explain like this in a simple way. Suppose I am talking about this curve. This curve is touching the nose of the C curve or not? This curve is touching the nose of the C curve or it is not touching?
सर स्क्रीन शो करनी.
Again, there is a problem. Okay, so there is no internet right now. I don't know. Okay, I'll stop the discussion here. I'll not show you the slide. But you understand, whenever you are drawing any cooling curves, you try to superimpose the cooling curve on the Ttt diagram, and the cooling curve is not crossing the first line, first Ttt curve. That's the transformation start curve. That means if it is not crossing the first curve of the Ttt, that means there will be no transformation of this austenite to perlite. It is okay if you are doing continuous cooling.
Yes, sir.
That means if the cooling curve is just passing away through the nose of the curve, it is not touching, or if it is touching, it is not crossing, then martensite formation will be easier. It is okay? That is the answer here. So the answer is what? Martensite formation will be easier if we are dealing with alloy steels or high alloy steels as compared to that of the carbon steel. Why? Because the nose of the Ttt curve is shifting towards right. So when we are doing cooling the steel, even at slow temperature or at a low rate, the cooling curve will not touch the nose of the curve. Or even if it will touch, it will not cross. Because if it will cross, the transformation will start to the perlite, basically. So whenever we want transformation to martensite, we have to avoid the perlite transformation, right? So you understand hardenability of a steel means the steel must form martensite easily, right? Upon quenching or upon slow cooling also, it should form martensite, and martensite should form everywhere. It should form on the surface as well as it should form on the center or at the core, right? If everywhere martensite is forming and you are doing slow cooling, then it is a good hardenable steel, or steel is having high hardenability. But if the steel is forming martensite only at the surface and not it is forming martensite at the center, then it is poor hardenable steel. It is okay. That's why it is susceptibility of a steel to get hardened by forming martensite, or it is the ability of a steel to get hardened by forming martensite throughout the cross section without drastic quenching. So tell me another important, let me ask you another question. Suppose you have a carbon steel and you are doing quenching, and you have an high alloy steel, you are doing quenching, and the hardness will be uniform, in which case? From the center to the core. Hello?
Sir, repeat the question.
You have one piece of steel which is carbon, you have another piece of steel which is an high alloy steel, and you are austenitizing and you are quenching the two sample, right? So in which case you will get uniform hardness throughout the cross section? Nearly uniform hardness you will get throughout the cross section, in which case? In carbon steel or in alloy steel or high alloy steel?
Sir, high alloy steel.
Alloy.
Yes. Why? Why? Just few minutes before I have explained. Why high
in
alloy
alloy
steel?
steel will not touch the nose of the circle.
Yes. So what will happen?
Sir, then throughout the cross section,
Very
martensite
good.
will form.
Very good. Very good. So that means throughout the cross section you are having martensitic microstructure. But in case of carbon steel, what will happen? At the surface, martensite will form, but at the core, or chances the fine pearlite will form. But condition applied, it should be a thicker thickness steel, right? But if it is a thinner one, then even at the core or at the center, you have martensitic structure, right? So in other words, you can say high alloy steels have high hardenability characteristics, due to which everywhere martensite will form. In every cross-sectional area, martensite will form, so it has uniform hardness. But in case of plain carbon steel, it has poor hardenability, right? Due to which the surface become hardened due to formation of martensite, but at the core, pearlite will form. But condition applied, it should be of thicker cross-section. That's all. So I will end the topic here. I will continue the lecture from the next class. So if you have any doubt, you can ask me right here.
So does high carbon content and low carbon content steels have different hardenability?
Obviously.
Okay, sir.
Carbon is a which kind of stabilizer? Carbon is a which kind of stabilizer? Ferrite
Sir,
or
austenite.
austenite stabilizer. Very good. Okay, I'll stop the topic here. You can leave.